Good morning, everyone. Am I audible?
Good morning, sir. Yes, you are.
Okay. Any doubt from the previous lecture? Okay, so let us start the lecture and let us start the lecture straight away with a question. So, what kind of filter is this system? So, this is a discrete time system, and you have to tell us what kind of filter does this discrete time system represent. So, in this, before even attempting this question, I want to make few remarks. First remark is that if you have an LTI system, right, its impulse response is its complete characteristic. That means if you specify its impulse response, then you tell everything about the system. So once you know the impulse response, frequency response is also known, right? So from h of n, you can calculate in case of discrete time h e j omega. In case of continuous time also, you can find its frequency response once its impulse response is known. Once you have a frequency response, and you always have it for an LTI system, that means this LTI system acts as a filter, right? So every linear time invariant system is a filter, some sort of a filter, because it has got a frequency response, right? So in case of discrete time systems, also you have four, five kinds of filters: low pass, high pass, band stop, all pass. What does this mean? How would the filter response in a discrete time system look like? So you know that if it is low pass, it would be something like this. So zero frequency, pi frequency, it would go minimum, it will attain its minimum value at pi frequency, and from there onwards it would increase, right? It would again get maximum at 2 pi, and then it will repeat because it's periodic with 2 pi, right? So if you specify this in one period, you know it in every other period. So it's a periodic thing, it keeps on repeating. So if the filter response for a discrete time is like this, that means it's a low pass filter. It passes low frequencies. Low frequencies are where? At around 0. And it doesn't pass high frequencies, which are at pi. So this is a low pass filter response. Similarly, for high pass, the response will be something like this. So this is 0 and this is at pi, 2 pi, and again this is periodic, so it will repeat. So this is a high pass response. Okay, similarly, you can think what would be a band pass response, or what would be an all pass response, and what would be band stop response, right? Now, one more point. H ej omega is a complex quantity in general, right? So when I am plotting these nice curves, it simply means I am looking at mod of H ej omega. This is the quantity which is of interest. So from H ej omega, you should plot this mod of H ej omega, and then you should see what kind of function is this mod H ej omega versus frequency. This thing, mod H ej omega, characterizes a filter, not the phase. Okay, not the phase. It's magnitude is what characterizes a filter. This you have to keep in mind. Now answer this. What kind of filter is this system? Yeah, what's the answer? 1, 2, 3, 4. So the correct answer is it's a high pass filter. Okay, let us see how we proceed with this question. So suppose you have this system. Okay, the first thing is to find out this impulse response, right? That is the first thing. What is impulse response? Input is impulse. That means xn is delta n. If you substitute xn as delta n, yn is hn. We know this, we have played this trick several times. That is the way we can find impulse response. So impulse response is this, substituting xn as delta n. Now once hn is known, hej omega is simple, right? What is hej omega? Hej omega is summation hn e to the power minus j omega n for all values of n. Right? This is hej omega. We have seen this. So now it's a very simple exercise. What we did is we have taken this instead of h of n, we have just taken h of k. It doesn't matter. It's just a different variable. And we have multiplied this with e to the power minus j omega k, and we have taken all values of k. So this will give us frequency response, right? Can we solve this thing? I think it's very easy. So, you know, delta k into this thing is simply 1, right? Because delta k exists only for k equals to 0. It doesn't exist for any other values of k. So when k is 0, this function becomes 1, right? So this multiplied by this simply gives us 1. Similarly, this will be 1 when k equals to 1. For all other values of k, this will be 0. So when k equals to 1, this function becomes what? E to the power minus j omega. So h e j omega is very simple. Okay. Now once you know this, we can arrange this in nice form. So what I have done is I have pulled out e to the power minus j omega by 2. So to get 1, I need to multiply this with e to the power j omega by 2. Right? I have to compensate for this negative sign. Then minus, to get e to the power minus j omega, I have to multiply this with e to the power minus j omega by 2. Right? So these two terms will make it e to the power minus j omega. Now this we know it's very known signal, right? So I can express this in sine omega by 2 form. So I can write this thing as this. Okay. Once this is known to us, we have to find out mod of h e j omega. So mod means this will cancel and this will also cancel. So simply this is some function of some sine function, right? So if we plot sine function, this is like this, right? So it's 0 and at pi, not pi. So where would this be 1? So
2
omega
pi.
by 2 has to be what? Pi by 2, right? So omega has to be pi. Okay. So at pi frequency, this is 1 and then it will decrease. So what kind of filter is this? It's a high pass filter. It passes high frequencies. Where are the high frequencies? Highest frequency is at pi. So it's a high pass filter because it passes high frequency much more. Right? Any doubt?
So can you repeat the condition for high pass filter once?
High pass filter is it passes high frequencies more. Highest frequency is what? Pi is the highest frequency, right? So this is my high frequency. This is my low frequency. This is my low frequency. You remember that?
Yes, sir. Yes, sir. Got it.
So if you look at this, it passes highest frequency much more than the lowest frequency. Okay, so it's a high pass filter.
So suppose pi by 2 at pi by 2 it was the maximum, then
Suppose it is maximum at pi by 2. And then what do you assume at pi? 0?
yes.
If you're assuming like this, then it is a band pass filter. It passes its highest frequency is at the band of frequencies around pi by 2. So it is a band pass filter. I can draw the diagrams again if you have any confusion. See, you have low pass filter which will look something like this. 0, pi, 2 pi. Okay, low pass filter. If you have a high pass filter, this will look like 0, pi, 2 pi. High pass filter. If the maximum transmission is at some other frequencies, let's say like this, band pass filter. Okay, so what we are looking at, mod of Hej omega, that is important. And then for all pass filter, it is like this, all pass. What is remaining? Band stop. Band stop will be inverse of band pass filter. So band stop, let me draw it here. Band stop is like this. Okay, band stop.
Sir, like in the
Yes,
case
sir. Got
of
it.
band pass, even in then there is a range of frequency that we are not passing in between. So isn't it like band stop in that sense?
No, band stop and band pass, the difference is band pass filter will not pass low frequency and highest frequencies. You see, so the lowest frequency is 0 and the highest frequency is pi. Okay, so band pass filter is the filter which does not pass the lowest frequency and highest frequency, but it passes some frequencies in middle. Band stop, if you look at this, it passes lowest frequency and highest frequency with the maximum amplitude. Okay, but it doesn't passes frequency in middle. So that is the difference between band stop and band pass filter.
Yes, sir. Got it. Thank you.
Any other question? Okay. Now you didn't have to do all this exercise to answer this question. You could have answered this in another way else also. What kind of system is this? If you look at the system, yn equals to xn minus xn minus 1. What kind of system is this? It's a very known system, right? What is the system? Okay, dyt by dt xt minus xt minus h divided by h. If h is 1, if h is 1, then you get this, isn't it? Sorry, this has to be yt. Yeah. So this system, you know, what is this system? What
Yes,
is the
yes.
system? Differentiator, right? So this system is a differentiator. And we have seen the continuous time differentiator. Continuous time differentiator is a high pass system, right? We have seen the frequency response of a differentiator in continuous time is j omega. It's a high pass filter clearly. So a discrete time counterpart should also be high pass. Okay, so there is some relationship between continuous time systems and discrete time systems. So you can always connect this in that way. All right. Let us look at now this system, and everyone has to answer what kind of system, what kind of filter is this system? Everyone attempt. You can use the previous strategy. It shouldn't take that much time. What kind of system is this? It's kind of an integrator, right? Integrator integrates from minus infinity up to t, continuous time. But here it's an average filter, right, which is integrating just over two samples. So it has properties similar to integrator. So from that perspective, answer should be low pass filter, opposite of differentiator. And let us see this more concretely. So frequency response, I will not now repeat all the steps. This would be the impulse response for this system, right? And frequency response can be obtained like this. And again, this multiplies by this to give us 1. And this multiplies by this to give us plus e to the power minus j omega, right? So this is the frequency response. Now you can arrange this in some ways like before, and you would get a function cos omega by 2, right? Just as we arranged the last one, here if you will arrange, you will get cos omega by 2. Cos omega by 2 is like this. Okay. So we are looking at this mod. So it's a low pass filter. Everyone gets this? Yes, no.
Sir, I think like just a quick doubt. Like it's low pass because between like pi to 2 pi, that also frequency is decreasing between pi to 2 pi, right?
Yeah. So low
So
frequency, high frequency, low frequency, frequency increases and frequency decreases. Okay.
yes, I got it.
Got it? Is there any other doubt? If you got it, you just have to say loud yes.
Yes, sir.
Yes, sir.
Got
Yes,
it.
sir.
Yes, sir.
Okay, good. Now, so what kind of filter is this system? This is complicated. Why is this complicated? Because this is a constraint system. Previous systems were recipe systems. Finding out impulse response was easy. Now, this is slightly tricky. And solving them is also difficult. So, how should we proceed? So, I do not expect an answer from you at this stage for this question, but it's an important thing to understand how would we proceed in such cases. Different strategy I will use. So let me look at the strategy. So the answer is it can act as a low pass filter or as a high pass filter depending upon this value of A. Okay. So A is unknown, and if you choose A properly, you can either make this as a low pass filter and as a high pass filter. So let us see the answer. So this is the system. Now the strategy that we will follow here in such cases is, we know that this is a linear time invariant system. Okay. If someone is asking you what kind of filter is this, then you have to assume it's a linear time invariant system. So in linear time invariant system, if input is e to the power j omega n, what is the output? What is the output?
H omega e to the power j omega n.
H e j omega multiplied by e to the power j omega n. E to the power j omega n we have proven is an eigen function of a linear time invariant system. And this thing we will use in this question. So we know if we make xn as e to the power j omega n, we can choose xn to be whatever, right? Then we know yn will be h e j omega multiplied by e to the power j omega n minus a times this quantity. What would be this quantity? This is simply clear. This equation is clear. If this equation is known, then you can simply find what is h e j omega, right? So h e j omega minus a times h e j omega e to the power minus j omega is 1, right? I just have cancelled out this term. This term I have cancelled out from the three parts, so we get a nice equation like this. Once this is known, h e j omega is simply 1 divided by 1 minus a times e to the power minus j omega. Is this okay? A
Yes,
different
sir.
strategy we have invoked. Yeah.
So you can also just do it, I think, like make it 1 minus RA and then divide that and then
Exactly.
substitute R with
Exactly. Yeah, yeah.
power.
You can use polynomial thing also, right? Absolutely. So now what should we do? So once we know this frequency response, which I have here, so it's nice just to multiply numerator and denominator with this function. So I can also write it in this form. Both forms are equivalent. Okay. Now I will introduce some concepts here before we proceed further. And concept is, it's very hard to avoid mistakes. So actually what we are interested in is mod of Hg omega. So this equation is slightly ambiguous. What we are interested in is mod of Hg omega. Mod of Hg omega, if we have to find this, it is mod of this quantity divided by mod of this quantity. Okay. I think it's not very clearly written here. So this thing is magnitude, in simple terms, magnitude of numerator divided by magnitude of denominator. Okay. So again, understand what we have to find out to find the kind of filter. It's magnitude of frequency response. Magnitude of frequency response is magnitude of numerator divided by magnitude of denominator. Now, instead of Hg omega, for a moment, just for a moment, think about its Z transform. So if I have written it like this, in terms of Z transform, it would be this. What is the relationship between Z transform and frequency response of Fourier transform is, instead of e to the power j omega, this quantity, what we use is Z, right, in Z transform, where Z is R times e to the power j omega. R is any number. Okay. So if I would have written the Z transform, this Z transform would turn out like this. Clear? Now, if you look at the numerator and think it like this, think the numerator, though it is not in that form, but let us think the numerator as this. Yeah. Okay. So I am writing numerator in this form, Z minus Z. So the product of the terms Z minus Z naught, and denominator is product of the terms where one component of this product is Z minus P naught. So this Z naught is known as zeros and P naught are known as the poles. So understand what I am saying. If I have h of z, I can, so h of z is normally numerator divided by denominator, and numerator and denominator I have factorized in terms like this, right? The roots of the numerator are known as zeros and the roots of the denominator are known as the poles, right? So if I look at this expression, what are the roots of the numerator? Where is the roots of the numerator?
0.
Yeah. So let me have a Z plane. So what I'm drawing is Z plane. So at 0, I have put in a 0. So this is the symbol for a 0. And for a pole, this is the symbol that we will use. So this is a 0 and this is a pole. Where is the pole? Where is the pole?
A.
A, right? And A, let us assume as 0.6 for this case, because A is unknown, and let us assume A as 0.6 for simplicity. So let me put my pole somewhere here. Okay. Now we are investigating this h of ej omega, and we know that to look at the frequency response you have to move on the circle with radius 1. Okay, so if you have this point, you can move on this point on this entire circle and you can get hej omega. Now if I look at, so I hope everything so far is clear, zeros, poles, Z transform and so on and so forth. So now I have to investigate these two quantities, magnitude of numerator. So let me just choose omega equals to 0 for simplicity. So omega equals to 0. So to find out the magnitude of the numerator, you have to find out this thing, right? This length. Magnitude of the numerator would be the length of this point from 0. There is only one 0, simple case. Okay. So if I want to find out the magnitude of the numerator, in this case, this is 1, right? If you find this is 1. And you can also find out 1 as the length of this 0 from this point. Clear? Now let me choose a different frequency here. Now its magnitude from this 0 is again this length, which is again 1. Clear? Now to find out the magnitude of the denominator, I have to find out the length. If I'm finding out the magnitude of the denominator at omega equals to 0, then this will be the length corresponding to that. And at this frequency, this will be the length corresponding to that. This is okay. And to find out magnitude of hej omega, what I need to do is, let me call this the first. So what I'm essentially talking about is, will be clear if I just remove everything, because I have nice pictures for it, which will make it extremely clear. So let me remove all this. So it's an important concept. If something is unclear, you have to ask. So to think about this, what I am saying, there is a 0 which is sitting here. Okay. And suppose I am finding out mod of hej omega. So what I need to do, on this axis I have omega. Okay. So first I have to find out this magnitude of hej omega at 0 frequency, 0 omega. So when I have to do this, sorry, so this length divided by this length, that is the magnitude of hej omega. And if you work this out for a equals to 0.6, you get some number as 2.4. Now if my omega increases, let's say to this point, this length remains constant, is unchanged, right? Because this is always the radius of the circle. What happens to this length?
It increases.
Sorry, I think there was some problem. Am I audible now?
Yes, sir.
Yes, sir.
Yes, sir.
Yes.
Okay. So where was I? Yeah. So what I was saying, I will go back slightly. So I have to find this mod of HEJ omega as a function of frequency omega, and let us now fix omega as 0. So omega 0 means I have to investigate these two quantities for omega 0. So that means, so omega 0 is here. So this length is constant divided by this length. This will give us magnitude of HEJ omega. Okay. Now what I do is, now I increase my omega. So my omega is increased. So the length, this length remains constant because this is the radius of the circle. This will always remain constant. Divided by this length will give us magnitude of HEJ omega. This length will increase, as you can see, right? Compared to this length, now this length will increase. Hence, magnitude of HEJ omega will decrease, which it has decreased. So you can imagine the frequency response to decrease as omega increases. Okay. When omega equals to pi, this length from the pole onto this frequency is maximum, right? So you will have the minimum value of mod of HEJ omega. Clear? Now if I further increase my frequency, this length will keep on decreasing. Okay, and hence my mod of HEJ omega will keep on increasing. Is there any doubt on this part? Is there any doubt?
So when will it be a high pass filter then?
We will come to that. But first, is there any question on this part? Is there any question on this part? Is this clear? This way of thinking about the frequency response and arriving at different kinds of filters?
Yes, sir.
Yes, sir.
Okay. Now let us look at the second case. When my A is 0.6, minus 0.6. Okay. This part, if you have to find mod of HEJ omega, what would happen? You know, this length at omega equals to 0 will be maximum, right? And as my omega increases, my length will become shorter and shorter, isn't it? And at omega equals to pi, this will have the shortest length. If this has the shortest length at omega equals to pi, my magnitude of HEJ omega will be the highest, because again, magnitude of numerator remains constant. So if I am plotting mod of HEJ omega, it will be some function like this. So it will be highest where? When omega equals to pi. Why? Because this length is the shortest. When would this mod of HEJ omega be minimum? When omega equals to 0. Why? Because this length is the maximum. Right? So this filter, this system can act as a low pass filter, or it can act as a high pass filter, depending upon where you choose your A. So this also gives us some idea of filter design.
So wouldn't it be a all pass filter for A equals to
Yes.
0?
What? A equals to 0, of course, all pass filter. And you do not have to do anything. A equals to 0, then this becomes S, which is 1. Right? A equals to 0 is straightforward, all pass filter.
So if A is greater than 1, then can it be a band pass or band stop?
You think, right now I have given you some tool. You think what would happen when A is greater than 1? You keep on thinking, and one more thing you think. So let us assume, I will not answer all the question at this moment. Suppose my A is here. If my A is here, not on the real line, somewhere else, is this a possibility? Can we have frequency response like this, where A is somewhere not on the real line? Okay, you think these questions are important, and we will answer them at a suitable time. Okay, once you have some more maturity. At this point, what I'm focusing on is, given that you have some sort of frequency response, if you can find out the poles and zeros of this frequency response, and if you can use this geometric interpretation, then sometimes your life will be simpler. You can immediately answer what kind of filter is this. Okay, let us do one more case. What about this? So pole is at A, okay, and 0 is at 1 by A. What kind of filter is this system? A
I
is a
think
real number.
again can be both low and high.
No, this will not be both. It will be either low pass, high pass, all pass, band pass. One kind of filter. Which one is this? Isn't this interesting that by selecting our poles and zeros and their locations, we can design different kinds of filters? Okay, so just randomly play out by different positions of poles and zeros, and you arrive at different kinds of filters. It's an interesting thing. The answer is it's an all pass filter. Okay, and I will leave the geometrical interpretation to you because I want to introduce different flavors, right? What I would do is I will simply use some maths to see if we can find out the filter response without using geometrical interpretation, but I request every one of you to also use geometrical interpretation for this question. Okay, and you can probably post this everyone. Use geometrical interpretation. Answer I have told you is an all pass filter. Something happened. My slides are not moving, right? Yeah, now it's fine. So HEJ omega is this. What I have done is I have pulled out 1 by A, and this thing becomes like this, simple arithmetic. Now again I have done a simple step. I have pulled out e to the power j omega, and I get this factor. Okay. If I take magnitude of Hej omega, this thing gets killed out. You will have 1 by A remaining there. What is magnitude of this part? It's 1. Why? Because this is nothing but complex conjugate of this thing. You can see it.
So here we'll have to
So
assume
numerator
that
and denominator are.
here we'll have to
Sorry?
assume that A is real.
Yeah,
Hello?
A is real. That is given,
Yeah.
right? So yeah, A is real. That is given in the question. If you look at the poles and zeros, A is real. Everything is on the real line.
Okay. Right.
Okay. Yeah. A definitely is real. So that is what you have to assume. So this part is complex conjugate of this part. So the magnitude of numerator and denominator for this part is same. And thus mod of Hej omega is simply 1 by A. Now let us look at effect of an all pass filter. So all pass filter, the filter that I have designed, it's an important filter in filter designing. Its magnitude frequency response is constant. However, if you analyze its phase response is something like this. Okay. So let us try to see what happens to our signals if it passes through such an all pass filter. Okay, which has got a constant magnitude response. Phase response might be something like this. Clear? So first analysis that we will do in the time that we have is for the music signal. So I will have an all pass filter which was created by the design that I have illustrated, and I will see the impact on the music signal that this all pass filter creates. Okay. So let us play out 4 sounds. The first is the music signal without any all pass filter. So music signal as it is. Okay. Then I will play music signal which passes through this all pass filter. So no distortion in magnitude response, but distortion in phase. And we will hear that. Then we will also play out some speech signals, a simple speech like bat, without phase distortions and with phase distortions. Without phase distortion means playing out the speech as it is. With phase distortions means that I pass this through an all pass filter. So there is no magnitude distortion, but phase gets distorted, and we will hear out these 4 files. Okay. Clear? Now you know where we are and what are we trying to do? Okay. So again, to summarize, we have seen different kinds of filter designing: all pass, low pass, band pass, not band pass, all low pass, high pass, all pass. And we have seen that by suitably choosing the locations of poles and zeros, we can create different kinds of filters. Okay. Now I am focusing on a specific kind of a filter, all pass filter, and we are trying to understand how music responds to these all pass filters. So let us hear first music without phase distortions. So now you know what is the original music. Now we will do these phase distortions and we will hear it again. What did you notice?
It was a high pass filter, I thought.
So the first thing that we notice is music remains tangible. It's understandable. It's comprehensible, right? Even if you hear the music with phase distortions, you can probably tell what sound it is playing. That means there are not much distortions, okay, when we change the phase of the music. Okay, so this is the idea. When you do phase distortions to a music signal, the music remains completely tangible, completely comprehensible, completely understandable. Of course, there was some noise that is produced, but it's kind of a noise, and if you do some signal processing, possibly we can alter it. So let me hear the music again. Right, so I agree, right? Music doesn't show that much changes to phase distortions. It just got some noise, but music remained completely comprehensible. Okay, is this okay?
Sir, so here did we apply any filter?
What, Avinav?
Did we apply any filter for this music?
Yes, yes, of course. The filter that we applied for this case is this filter. This filter.
Oh,
Okay, so actually this filter, what you have here, we just applied that filter, so its magnitude remains unchanged when this passes through this LTI system, but phase distortions happen. So we are looking the effect of this filter on music signal.
okay, sir.
Okay. Class, lift yourself, say aloud yes or no. Did you understand what we are doing?
Yes, sir.
Yes, sir.
Bad.
Look at the speech.
Bad.
Speech without phase distortions, speech as it is, speech with phase distortions.
Bad.
Again, what you see is even speech is comprehensible. Okay.
But why was there
So
an
there
echo?
is, sorry, yeah, there is some echo, but it's comprehensible, it's intelligible, it's tangible,
Is
it's
that due to
comprehensible,
this filter?
understandable. Abhinav,
Sir,
I
is,
don't hear you. You probably seem to have some.
sir, is that due to the filter, that echo?
Yeah, so the phase distortions for a speech signal produces some sort of echo, and we will possibly understand this. So we have shown these effects, and I will like you to think about these effects yourself, and we will come back and discuss these effects in the next lecture. Okay, we will have the demonstration again, and we will see the reason why the speech and music signal behaves like this on phase distortions, and then we will see the effect of these things on images. Okay, and you will see very different effects. You will see that images are very sensitive to phase changes, whereas music signals are not. We will
Sir,
continue with this theme in the next lecture. Yeah, Siddhant.
sir, what is the utility of all pass filters? As in, if it allows every frequency to pass, then how is it a filter?
Utility of an all pass filter we will see next time. So suppose you have a filter, just one thing. If you have an all pass filter and suppose you have an image, if you pass this through an all pass filter, the kind of filter that we have shown, the image gets completely distorted. Completely, you will not have any sense of that image left, because images are very sensitive to phase distortions. That means you can take an image and you can distort this, and let us say you have image tilde. So if someone looks at this image tilde, you have no sense of what this original image is. So possibly you can use this technique to store your images in the computer so that no one can see what the original image was, right? So suppose as a student and you do not want your parents to see what sort of images you are storing in your computer, you can write a simple MATLAB program, alter the face of images, store them, and then your parents, when they open it, they will have no clue of what images you are storing, right? When you have to get back this original image from image tilde, you can change the face distortion because you have created a known face distortion. You can always undone it and can get back the original image. So one utility that you can make use of by using face distortion. It's used in encryption and in storing files safely.
Understood, sir. Thank you.
Okay. Okay. Any other question? Okay, then see you all tomorrow. Tomorrow also we have a class. Take care. Bye bye.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.